And so we have a question that says, how do I know which molecular orbital or p orbital lone pairs will be in? You'll have lone pairs in a p orbital only when they're next to a double bond. So let's just imagine kind of any atoms that are forming a double bond, and to be even more accurate, I won't even do both X's because they don't have to be both carbon carbon. They could be something else. And then the atom over here, this lone pair here, could be in a p orbital. So that way it can resonate by bonding into this X molecule, doing a double bond here because there's already p orbitals in this atom and in this atom. That's why we have the pi bond there. And so your question is, well, what orbitals is this in? That matters based on the Lewis structure. And so let's look at some examples for a second. So this most commonly happens with amides. And so here I've drawn an amide, and these electrons are in a p orbital. And so if I think about there being an XY plane on my board, Y and X, I notice that my bonds on this Lewis structure are using Y and X. So PX and PY are being mixed into the sp2 orbitals. sp2, sp2, sp2 for that bond, sp2 for that bond. And then these p orbitals are in a pz. Let's draw it another way to put to again draw the Lewis structure in a unique way that shows it in another orbital. So C double O out to Rn here. And let's have it wedge out to our N. And maybe our N sends back an H that way. And we'll put it there, coming straight out and straight down. So now these orbitals here are using Z anytime we have wedges and dashes. So I must be using a PZ in this sp2, sp2, and then sp2 down here. And the line here is showing me that I'm using P. Well, let's check the graph. Put the graph on there. There's Y, there's X. That bond is on the PY. So in this case, my P orbital that's mixing in is my PX orbital. And that's mixing into it. So it's a tricky question because the short answer to your question is you have to look at the Lewis structure. The long answer is to even look for this in the first place, we need to look for two electrons next to a double bond. That's a pretty common motif that we'll see on the exam. And then there's an example of it being PZ, and there's an example of it being PX. .1 exam resonance question. Let's see if I can find it. While I'm trying to find it, will you type as much as you can about it? Let's see what we find. Oh wait, no, I know where to find this. Draw the two best resonance structures for this molecule and connect your structure with the appropriate arrows. Be sure to show all additional bonds, lone pairs, and formal charts. Neatness counts. Okay. All right. So we are looking at carbon connected to a hydrogen, connected to a hydrogen, connected to a hydrogen. Then we go out to, let's do a blue nitrogen, and then they give us a line to another nitrogen, and let's keep the bonds yellow. Okay, so this is what they give us, and first thing we need to figure out is how many valence electrons are missing. And so for hydrogen, we should have 5 for each of them, so I'll tally that up to 15, plus carbon bringing 4, plus hydrogen bringing 3. So we should overall have, 22. And so far in the structure they've given us, I see 2, 4, 6, 8, 10, 12. And so that's me counting all of the yellow lines. Each line counts as 2. And so I'll minus 12 from that number. Oh, come on, show the cool thing. And so for each one of these, again, I'm counting 2, 2, 2, 2, 2, 2, 2, 4, 6, 8, 10, 12. And so 22 minus 12 means I need to put in 10 more electrons. And let me see a second. Great. Oh, I must be counting something wrong. Let me check to make sure we're counting that right. 5, 10, 15, 19, 20, 21, 22. We've shown how many. No, I think that that math works out. So maybe there's, well, I guess I'm a little bit nervous about the key, but okay, let's keep at least trying to go after this problem. So we have 10 electrons that we have to put back in. For now, I'm just going to complete nitrogen's octet. So let's make some room. So we need to fit in 10 more electrons. So let's start by putting in 1, 2, 3, 4, 5, 6, 7, 8, maybe 9, 10. And well, already I know this probably won't work, so I'm going to put my 4 over here to start. And now I got to start moving some electrons in to actually make my bonds. Maybe this has already happened earlier in the problem, but I'm noticing that this nitrogen in here does not have its octet filled, so I'm going to fold in those 2 bonds, and let's also fold in these 2 over here as well. And so now we're left with one possible Lewis structure could be CH, H, H, double bond to an N, double bond to an N, 2 electrons out here, and it looks like I have 2 left over here. Oops. And then I'll go through and do formal charge, 5 minus 4 minus 1 minus 1. So this is a -1 nitrogen out here. Nitrogen 5, so that's a +1. Oh, and I broke the octet rule. So, or no, I didn't break the octet rule. I copied it wrong. Okay, that nitrogen moved its 2 in. Okay, and this nitrogen is neutral. So this is one of the Lewis structures, and the key has an error, it looks like. The nitrogen here should have a lone pair attached to it because they're missing some electrons in their key. But, okay, so then now we need to think about a resonance structure. So over here, I do have a atom that are bonded to one another here, and then there is another compound over here with that lone pair. And so either I move this one in and this one out would be one answer for a resonance structure. And let's see what that looks like. So one option is to have my CH3, 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 going to an N now. Oops. Going to a triple bond to this end, out to this end. 1, 2, 3, 4, 5, 6. All right, so now, though I'm not sure if I like this Lewis structure, but it's an option. So the what I want to kind of impose about this, and okay, one question: why did you arrange the electrons like you did? I would say it's really trial and error. I'm assuming you're asking about what I did here when I was just putting them in. It was mostly trial and error with my goal of thinking about octet was important, that I wanted to make sure everything got an octet, and then I just kind of put in electrons. And part of what makes Lewis structures fun, if you can call them fun, is they are a measure of how many different ways can you put something together following some general rules, but it really comes down to what I'm always checking more automatically in my head than certainly students are, but octet rule and formal charge. I'm calculating likely a little bit faster than you, but certainly you can look at any of my structures, pause, and consider the octet and the formal charge. And so that's why I don't like this resonance structure already, because I've gone for this resonance structure here. This is the, well, I guess this is the first structure I drew, and I liked it because it was only plus and minus on two things, seemed reasonable. And over here on number 2, for example, became less reasonable. So what is option number 3, and how did the key give us one of the right resonance structures? Well, I could make this one move in, triple bond, move this one out here. And so let's look at the result for that one for a second. Triple bond to an N, single bond to an N with 2 nitrogens on it, and then out to a CH3. Why do I like this one better? Because I'm now changing my perspective to saying there's the double bond, one bond away, there's a lone pair on that atom I can mess around with. So it's following in either a nice way or a not nice way. This pattern is something I'm looking for. You know, whether this is a bond or a double bond, there can still be moving electrons through those systems. And let's go back down here. Why do I like this structure? Because over here neutral, over here positive, over here negative. So this structure was not good because I had more formal charge than I needed. And so these two structures, the first one I drew somewhat haphazardly, or in some method of just trial and error. And then 3 was a good resonance structure of it because it maintained the two charges, negative and positive. And again, I would say that I came at this with a lot of experience with thinking about these molecules, and drawing this first Lewis structure is not necessarily going to be a piece of cake, but the fact that the exam at least gave us the bonds in yellow made sure that we knew we were stacking electrons into the nitrogen in some form. And try as we might, and that is part of, I think, practicing, is putting in electrons that, and seeing if you can ever get no formal charge. There's no way you can put something in here and get no formal charge. Okay, I'm still a bit confused on hybrid orbitals and resonance. Can we do 5 for that same exam? Yes, we can. So 5, we're looking at a pretty complex molecule, but the good news is we can split it into pieces. For the most part, if there is an egg that is 3 or trigonal planar, that's going to be sp2. If its egg is 2, it's sp, it's linear. If its egg is 4, tetrahedral type, then we're going to call it sp3, unless we're going to keep our eyes peeled for any double bonded atoms connected to some atom that has that lone pair. We're going to want to investigate those a little bit more carefully, but that'll be a general strategy for figuring out what hybrids are. The tricky part, and kind of what your first question here as we started talking, was about hybrid orbitals and what is their orientation, which orbitals are we mixing in. Again, it comes down to the Lewis structure, and let's see if this question cares about it. So first one they're having us look at is our line structure shows a aromatic ring. It goes off to a bunch of nonsense, but we don't care about that nonsense, and we're looking at this atom here. In my head, I see a sigma bond and a sigma bond coming together, so I know there's a carbon there. There's also a double bond there. This carbon has a formal charge of 0, which most of our carbons should be, so I'm going to bring it up to 4 bonds. Count my areas of electron density, 1, 2, 3. So this would be sp2 on that carbon. I'm going to pause for a second as the stream catches up, and then let me know if you have any questions before I move on. Awesome. So let's do some of the other quote-unquote easy ones. There's another part of this molecule where we have an H and an O with two lone pairs on it, and it connects to a carbon, connects to a carbon. There's two H's on this carbon. But why I'm drawing this part of it is because I did notice a lone pair. I noticed some lone pairs. And so I just wanted to check over here. Is this a double bonded molecule? Because if it is, it's got p orbitals on it somewhere that might want to mix in with these ones. Our wave functions might want to mix that way. But there's not. So, okay, great. This is another quote-unquote easy one. Because I don't have that possible resonance structure, because I don't have a double bond here that these electrons can push out, I just get to do the same thing where I'm going to count the areas of electron density. 1, 2, 3, 4. So that's got to be sp3. And another, stop me if I'm pretty sure that should make sense a little bit. And then there's another one where we have this nitrogen lone pair going out to this. And they're asking how many hydrogens are here. Well, I know that this is a sigma bond ending at a carbon. This carbon has a formal charge of 0. So there should be, to get it back to its octet, should be 3 hydrogens there. Then the tricky ones. So we'll do the easiest of the tricky ones first. There is a N with a lone pair connected to an H, connected to a carbon that is sp3 hybridized. It goes out to that phenyl group over here. But okay, that's not something I'm worried about. That's not a double bond over there. But going down from the nitrogen, we do hit a double bond. And so these electrons here might be able to delocalize into this pi bond here because we have the setup of an atom with lone pairs connected to, in this case, if I draw in what's actually there, there's a carbon there, double bonded to a nitrogen. So there is, once again, kind of the nice central motif of our conversation right now is we got to keep looking for these lone pairs next to double bonds because this one can delocalize, and the resonance structure would be those red electrons coming into this carbon, and let's make these electrons green coming out and onto that nitrogen. And so it's a shame we're not formally teaching you yet arrow pushing, but that's kind of what's going on here, where there's the resonance structure that nitrogen now, when I look at its egg, is in fact sp2. Because that lone pair is the p orbital that I've left out of the typical sp3. Nope, it's sp2, and the other p orbital are these red electrons. So this is a tricky one, but the nice thing is it does continue our conversation of watching for atoms with lone pairs next to double bonds. And we're going to go right into another question on this one that maybe is causing you some concern, and it's a great one to go over. But before I move forward, to the trickier one, the two tricky ones. Would the addition of double bonds change the hybridization? Absolutely. So one kind of cool thing to think about is single bond, double bond, triple bonds. To have a triple bond, you need 2 p orbitals. Those p orbitals, it doesn't matter. We don't know if it's x or y or z. Technically, how I've drawn it, we know, but let's not get into semantics right now. There is 2 p's, either x, y, or z, that are making the double bonds. So the leftover bond must be sp hybridized. Remind yourself that all of these things should add up to 1s and 3 p's. 1s and 3 p's. This double bond, though, says that, well, I have one of my p's is being used to make this pi bond. And again, this p could be x or y or z. And the bond here is sp2 hybridized. And you may be asking, where are the other bonds? Well, they're going to be coming off of that central atom. But regardless, if we see a double bond, the atoms on either side of that, we do need to look at the entire picture, but a double bond in itself is using 1 p orbital to make one of the 2 bonds. And then back here with single bonds, there is no pi bond, so it's very possible that this is an sp3 orbital. Again, there is more semantics, more difficulty to this when we actually look at structures as we're about to, but the addition of a double bond must change the hybridization, because to make a double bond, you have to pull a p orbital. And if you're pulling a p orbital, every time you pull a p orbital, your hybridization change. sp3, if I minus a p orbital to make my first pi bond, then I go down to sp2. And if I pull another p orbital, I go down to sp, and there is now my double bond. Maybe that was a better way of explaining it. I don't know, but I'll pause there before I move ahead. And this might be a nice time to just remind ourselves that pi bonds, because they involve electron density above and below your atoms, that's why we can only use p orbitals to form these pi bonds, or at least what we need to know right now. Kind of over time, we're trying to have you guys move forward from, yes, we will represent molecules very simply like with these line structures, but to start having more enjoyment of chemistry, we actually need you to see the orbitals. Okay, so for the example, did you tell me which orbital they would be in and why? No, so we still have to do, well, for 5.1, based on that Lewis structure, so the Lewis structure is here to here. So this is 5.1. What is this lone pair's orbital? Well, again, yeah, and I might ask you, so if you see this bond and this bond and this bond, notice they're all in the XY plane and they're moving across the XY plane. So what are these yellow bonds using? Which p orbitals? And I know there will be a little bit of a delay. But we do. It is exciting to move into the more difficult question once we're ready. But we have to look at the Lewis structure on that page, and they're showing me all these bonds in the plane. Yep, I agree. X and Y, definitely. So just to visualize that for a second, what do you mean when you're saying that? Again, this nitrogen by itself has a py on it. It has a px on it, and it has a pz on it. And it also has its s orbital. So again, with nitrogen's configuration, we're starting to have space for our sp, our 2s and our 2p, with our p coming in three varieties: px, py, and pz. And so before hybridization, nitrogen by itself, we kind of think of it like, well, its wave functions are like this. Yes, we know this is not super accurate because it's going to start hybridizing these things. These waves are going to constructively add and destroy each other. And so when I say that we notice the bonds, we notice that the yellow lines are going across the y and x plane. There is no wedging or dashing. That's telling me that my s orbital, my py orbital, and my px orbital, I basically took my hand and I grabbed that orbital, I grabbed that orbital, and I grabbed that orbital, grabbed all three of those orbitals, put them in the hybridization whatever mixer, and then out came this. And so I'm going to just redraw nitrogen again. Or how did I do it? Let's redraw nitrogen again. I did it in white. Okay. So now I'm going to show you nitrogen, but I've done the sp2 hybridide. And so the sp2 took what colors? Red, blue, and green. I've taken the py, the px, and the red. So red, blue, green. So a combination of those three orbitals makes this sp2 orbital. There's kind of a version of it where you're seeing all three of the colors are now in there, and that's bonding to possibly some other atom. We don't know. And then there's another sp2 orbital based on the Lewis structure going this way, and it also has its little other end phase, and then it also has one pointing down. And so I've mixed the sp, spx, py all together. That's what these kind of multicolored orbitals are looking like. And so now I have three sp2 orbitals that have appeared. Let me kind of dot them. There's that one. Here's another sp2 one. It's not the best it's not the best hybrid orbitals, but I'm showing you that if we go back to the Lewis structure, we'll keep in the back of our head, the Lewis structure looks like this. Out to some carbon, down to some carbon that's double bonded. And so I'm just showing you that I see more than these lines. I see that I ate up certain orbitals based on the Lewis structure, hybridized them, but I didn't use the yellow Z. So the yellow Z is coming out at us and going behind. And if I was to make a double bond to that carbon through the resonance structure, then these electrons on nitrogen, based on my Lewis structure, have to be this pz that could not have been mixed in because there is no wedging or dashing. There is no Z character in these sigma bonds, so the Z character is where the lone pair exists. But that's the intensity of seeing orbitals versus seeing lines on a page. And absolutely, this is not something that you should be able to do without any system in place. But the Lewis structure is certainly the guide, and identifying when you have everything in the plane, when everything is a straight line, that is a key that you're likely using Y and X. If you start to see wedges or dashes, that's a sign that Z is getting involved. But it's a really neat process. And so before I move, again, I want to move on to 5.3 and 5.6 are both excellent questions. And again, if there's another student here, go ahead and pop in, and you can also ask a question. I can kind of go between questions as well, kind of like how I handle normal office hours. Give an example of when everything isn't in a straight line in the plane. At least, well, I guess for the most part, something likely has to be in the plane. The reason I'm saying that is based on the Vesper. So there's like a linear molecule where this is sp. So no matter what, I'm going to have single lines in the page. Same thing with sp2. I'm going to have some lines in the page at some point, even if I rotate it. sp3 will also have some in the plane. So it's here's a common thought, or a good like thinker molecule. One of the more tricky questions I've seen designed for this type of material. So here's a pretty infamous molecule where we have a carbon with two bonds to it on either side going to other carbons, and we'll notice that there is very distinct choices of certain bonds here being in the plane, and then certain bonds here being in the plane while also coming out of the plane and going into the plane. And so we might ask ourselves, what is the p orbital that this double bond is in? And so if I look at this carbon, I would say that it is using the SPX and the XPY, because my red bonds are certainly moving across the XY plane, so I know it's using those. So it must be using a PZ coming out of the page and going into the page back there to form that pi bond. And then over here on this carbon, I'm noticing that it's a little bit trickier because this is implying certainly that there is some px movement going on. But these wedges and dashes, I have to say, if I see a wedge or a dash, I need pz. So on this carbon, it is the py that's forming this double bond. So that might work as an example, but I don't think it's possible to give you an example when everything isn't in a straight line in the plane. But this is a great thought example because the Lewis structure on one side has all three red bonds in the plane. And then over here, you have only one bond in the plane, and then you have wedges and dashes. So maybe your question is an example of something with wedges and dashes, and this serves that purpose. And even if you want to take this a step further, if I'm saying that I used the py to form a pi bond with this carbon, so I used a py, check, and then over here I used a pz to form this one here, I must be using, let me see if I can get a new color. This is sp hybridized, and it's an X that's actually being hybridized to make the single bonds, which are, of course, traveling across the x-axis. Yeah, it's like we don't realize how much information we're talking about with orbitals when we put Lewis structures on the page. And so something as simple as this structure becomes a lot more complex when we start to consider the orbitals at play. Because this is what we show on the page, very simple, but that's how much thought goes into what the orbitals are. But it's all about where are the lines on the page. Again, wedges are signs of pz. The lines like this are a sign of px. And then this is a good example of a py and a px. And we maybe want to move on to 5.3 or 5.6, or maybe more questions on this one. Again, feel free to jump in with another question if you have one. We can kind of jump between topics. Awesome. So let's move on to finishing 5.3 and 5.6. So 5.3 is one where it's like, okay, now we are getting very, very tricky. So we have a N double bonded to a carbon, double bonded to a carbon with a double bond and electrons here. And so you may be saying, and I would want you to say this as well, these two electrons here, and there's a double bond over here. So what if I did something like that, moved that into there, and moved these onto a carbon, it looks like? The first thing we would start to see is that it's kind of an awkward resonance structure because you're claiming that this nitrogen, which right now is looking like it's sp2, and by moving this lone pair into a double bond, I need to steal a p. So you're saying this nitrogen would go sp. And what the example is showing as well is if we go out to a nitrogen, go down to here, this is in a ring structure. So there's a little bit of uncomfortableness about this resonance structure, not because of formal charge. Certainly that is already an issue, right? If we quickly look at the Lewis structure of me doing that resonance structure. So I took something with double bonds, moved it over to where there was a double bond, pushed those electrons onto a carbon because there wasn't. Oh, actually, I could push it further. I could resonate that further around, but I'll start with the point that it is awkward to make something in a ring have a bond angle of 180 degrees. Again, this is more of a what makes this question difficult is if you're grasping with bond angles of hybridization and seeing them in structures along with the many other things we're asking you to do, yeah, it adds to the pile certainly. But so that's one thing. That's one reason why I'm not sure if I want to resonate these electrons. And then we need to think about what do we know about these orbitals. So let's draw this with the orbital complexity that I've been showing thus far. So we have a nitrogen double bonded to a carbon, single bonded to a carbon that also has a double bond on it, going off to something else, and we have a lone pair here. So the first thing we want to say is, well, this thing is sp2 hybridized. There is 3 areas of electron density. So that nitrogen is already sp2 hybridized. And so if we were to do the resonance structure, it would be unique. We haven't seen a resonance structure yet where we go from an sp2 to an sp. So that may be some sign of something's a little bit different here. But again, I wouldn't say that's a final answer to what's going on, but this is a nitrogen that looks to be sp2. We're keeping in the back of our head, is it sp? Based on bond angles, I wouldn't suspect it to be sp hybridized, but let's keep digging into it being sp2. So if it is sp2, I want to ask myself, does the Lewis structure tell me which p's are being used? And in this case, it does. So I have my y, I have my x. These lines are indicative of py and px. So I now know that if I look at this structure, I'm going to say that these lines here and here are using spx and y to give me the sp2 that I see on this nitrogen. And the double bond then is the p that was left out. So I'm not using, so x and y I'm using to do these bonds. So this needs to be pz. And these electrons here right now then are in the other sp2 orbital. So what does this look like orbital-wise? We have a nitrogen where a lone pair is existing in a hybrid orbital. We have a sigma bonding sp2 orbital going down to a carbon. We have a carbon itself that has a pi bond, but we're just going to look at its hybrid orbital. So there's my 3 sp2s. There's one sp2 kind of in that area. Here's another sp2 in that area. And here's another sp2 in that area. And the pz is coming out at me, going away, and it's bonding towards this carbon here. And over here, I also have some information about this is, I know this is double bonded to another carbon. And so if I look at this thing's orbitals as well, because I have the sp2 orbital here that uses x and y, I know that this carbon is going to have a pz orbital coming out at it and going into the board. So there's my pz on that carbon next door to it. And so if I was to unhybridize this from sp2 and hybridize it to sp, I would need to bond into this carbon using one of its p orbitals if I am going to bond into it. But my pz is already aligned with my other pz. And so that lone pair in that case is in it is in an sp2 orbital. And if it was to hybridize, it would go into an sp orbital, causing significant angle strain in that ring, or just creating a structure and a resonance structure that doesn't seem to make a lot of sense. We have a nitrogen double bonded to a carbon. We won't worry too much about where the lone pair is. Going down to another nitrogen. Let me put that up there. And another one there. And so, again, we just want to consider, is that a reasonable bond angle? Probably not. I doubt that that is going to be 180 degrees. So I doubt it's going to go to an sp hybridization, but it's in one of the sp2 orbitals. And so if it's in an sp2 orbital, we know that resonance only happens with p orbitals. It's only the pz that's already double bonding to the carbon, the blue carbon down here, and not off to the, and not forming another bond. And so kind of a similar question then is being addressed well, I won't say that, but the other question is actually asking a very similar thing. So if we look at this carbon, nitrogen, well, let me make it a little bit smaller. We know this also rings around. So once again, we do have a situation of technically, yes, we could once again resonate this in, resonate this even over here, resonate it onto that nitrogen. There's all sorts of interesting resonance structures we can do. But once again, we're going to be invoking a sp orbital, a 180 degree bond angle in the Lewis structure. To me, as given, the Lewis structure does not at all support that this thing could be linear. Based on what I'm seeing on my picture, it has to be tetrahedral or trigonal planar. There isn't a straight line put on by the chemist who put this question, or who's developing this molecule, talking about this molecule. So I'm not going to hybridize it for the same reasons in that previous question. And so I have to ask myself, okay, what does this bond tell me here? Well, this bond is telling me that this nitrogen, which is sp2 because it's got 3 areas of electron density, and I doubt it's going to go down to sp, because I don't think that this Lewis structure supports it being 180 degrees. And so if I keep it at sp2, what are the p's being used? Px and py. And so this double, well, let me change colors. This double bond here is using the pz coming out and going away. And so this leftover orbital in the sp2, there is 3 sp2 orbitals. So when I make an sp2, I should find 1, 2, 3 areas of electron density that hold that. One is the single bond that's not double bonding. Another one is that bond to that carbon. And then these lone pairs as 2 electrons are existing in the last sp2 orbital. And in some ways, this is actually kind of a fun question, because when we were looking at this example up here from the earlier exam, when they put these nitrogens in a row somewhere here, they put those nitrogens in a straight line. To me, that tells me that this nitrogen might be sp. One of these nitrogens might be sp because the Lewis structure already has in it a 180 degree bond angle. So a nice callback to that previous example, and why I did end up with a sp hybridized nitrogen in both of my resonance structures, because I already knew in some ways by the Lewis structure they gave me it was going to end up linear. Whereas in these other exam questions, there's nothing about this that looks linear to me in the first one in 5.3, and there's nothing that looks linear about this one. If it makes you, feel a little bit better, at least when we're talking about that amide example, a lot of people will draw it like that to clue you into it being sp2. And if they do try and trick us by wedging it and dashing it, there is still the most common thing we would ever see is this amide bond forming a double bond to a carbon. And typically, well, not typically, almost, well, you can lock this into a ring, certainly, but having a double bond with 120 degrees that's more reasonable to have in something that will eventually become a ring than a straight line. So very, very tricky, and is asking a lot of students to know what p orbitals were left out, and then considering what is the result of transferring an sp2 to an sp, and does it match the Lewis structure in a reasonable way, I would be unsure about putting 180 degrees in what effectively is a 6-membered ring connected to a 5-membered ring. Neither one of these look like they want to have straight lines in them. And so looking at questions 13 and 14 on this exam. So 13, we're given this, and some p orbitals, And so what is this p orbital, or what are these p orbitals? Which one are they? Y, X, or Z? Yeah, yep, definitely py, yep. So these are py orbitals, because there's my y-axis. So one piece of information that we have to start with, and we'll highlight it, is that based on what's being given, these are both py orbitals. Awesome. Next question would be, what do you think, what orbital would be needed for this single bond? For sure we need the s orbital. The s orbital always comes, but what other orbital would we need? Based on what the Lewis structure is. So what can we glean from this example based on the Lewis structure already? And again, I know there's a delay, so take your time and be wrong. It doesn't matter. It's okay to be wrong. PX, yep. So we know that the sigma bond, which is some sp orbital, we know it's using px. So that's another piece of information that we have, is it's px. Now, they gave us they said that our Lewis structure is H2. Oh, I didn't even finish this. Is H2CO. They also told us there's something out here that we're going to have to bond to. So if I just theorize those two bonds, there and there and there, what more information do I know? Well, and I'll say this is the tricky part of this question. This is, why it's a good exam question, is first we need to kind of start to conceptualize, if I have two p orbitals overlapping, that's a pi bond. And so the first piece of information that we're going to put on here, besides the stuff we've already talked about, which is that we know it's px, we know it's py. I'm even going to get rid of the dotted lines for now too. But we know that there is the first piece of information we're going to add to here, and let me put this in, let's say pink or something that we might want to put on here. We might want to realize that that's the pi bond. That when these overlap above and below, this is what there's actually a double bond there. So that's the first difficult piece of information for me to conceptualize in my head, that that's going on there. Then if I look over here at these orbitals here and here, That is electron space. So I'm counting 1, 2, 3 areas of electron space. So the next question I want to ask you, I wasn't going to ask you, do you know it's a pi bond? That is what makes this a little tricky, seeing that double bond there in the Lewis structure, because they gave us 2 py orbitals. And we could even try and draw this Lewis structure off to the side and realize that this is the Lewis structure. It's not solving this question, but we do know that the hybridization on this carbon, well, I'll ask you, based on egg, what is the hybridization of the carbon in this Lewis structure? What is its egg? And then if you can bring that to hybridization, great. If not, no worries. Yep, it is. It is sp2. Awesome, awesome, awesome. So, okay, let's kind of then back up a little bit and say, why does that help us? Well, again, we're in my mind, I at this point I see this as it is a game, it is a Sudoku type kind of thing where the amount of information they've given us is good and we're just adding to it. So let's kind of now walk back to what we said. So first thing that we said, definitely on the page, px and py are pretty clearly used, and so the sigma bond is definitely using px. And then off to the side, I doodled the Lewis structure that wasn't going to answer the question, but did allow us to confirm the next piece of information, that is sp2 hybridized. Then we had to make, probably the hardest part of this is realizing that is, again, the pi bond, that's the double bond. And so what I am starting to realize is that this carbon, that white carbon, is sp2 hybridized with a py forming its pi bond. And because I said the sp2 is including the px, and I've already used the py, the key part to this question is what p has not been used. And I'll pause for dramatic effect. If you want to type it in before I say it, I'll probably beat you to it as you're typing it in, but I'm thinking about the 3 p orbitals, py, px, and the missing one, the question mark one, is pz. And so I'm starting to say that, oh, the sp2, the p2 in sp2, my focus is on what 2 p's. If I'm using a py to form a pi bond, I must be using px and pz in these. And so on the exam, we finally see that the answer is to show pz, we need to do wedges and dashes. Yeah, so you even got it. You know, I was dancing around it, but absolutely, that's the key to this problem. Is I think the answer key could be served by suggesting to students, once you draw the Lewis structure for this, right? If we just gave you C or H2CO and you try to draw a Lewis structure for that, you'll get the fact that this carbon needs to be sp2, and then we know that the px is here, the py is already being used for the pi bond, so something about these bonds needs to show pz and px. Why is pz? Yeah, great question. So when we are talking about a wedge, what is hard for us to see is that really the H is on top of the, well, I can try to do perspective. Really what we're saying with a wedge is not that the H is out here and bigger. Really, we are trying to show that this H is in front of the carbon, but think about how messy that would look. So we have to put it off to the side. We can't put the H's actually in front of the C's. So we put them on a wedge just to say that this is going out in front of it. And yes, there is a little bit of subtlety on sometimes these wedges do mean truly out, and sometimes they do mean out with a little bit of variation around it. But the fact that this is coming out of the page, it goes back to the coordinate plane being that on a piece of paper or on an iPad, there is only 2 dimensions. Try as I might, I can only make dots in this YX plane as I move all around with I can't leave the YX plane. So every time I draw a line on the page, that's using all Y, that's using all X between bonds, between bonds, between bonds. Or if I cross them like that way, that's now using X and Y. And so I need another access. I need another access to actually do what I did here, where I put a H in front of a carbon. And so the Z axis is the one that is actually coming out of the page and going into the page. That really, if I could accurately show it, it's actually coming out this way and going back this way. But it's very hard on this piece of paper to show that. If I try to utilize perspective to the best of my ability, be a tiny arrow going back there, and then this big arrow coming out at us, because that's really where the z-axis is, but I'm forced to do the best approximation we can do on a two-dimensional plane. And sometimes I'll dot it to remind myself that it's going backwards and coming forwards in my own work when I was first studying this material, but it's fine if you just do a straight line as well. But when I'm coming out and going back, that is a PZ orbital. That is what PZ gives us, because every single one of these atoms that we're looking at, this carbon, nitrogen, oxygen, fluorine, which is primarily what most of our bonding it contains, the electron configuration for these gets up to the 2s and the 2p, x, y, and z. And so on every single one of these atoms, I can draw everything on the plane if all my orbitals are just using px and py. But through the use of the z orbital, I'm able to get wedges and dashes. And yes, there's absolutely a more complicated conversation to say about, well, can't s orbital give you three-dimensionality? Absolutely. I am oversimplifying that these bonds really are in 3 dimensions, but for ease of looking at a Lewis structure and knowing what orbitals are being used, you have to kind of follow. Well, you don't have to, but I'm proposing you follow my method. I can't think of another way to teach it. Wedges and dashes have to involve PZ. But I understand. Well, why can't it use S? Because you're mixing them into the hybrid, I guess would be the simple answer. Can we go over the difference between constitutional isomer, conformer, and stereoisomer? Absolutely. So and I shouldn't say oversimplification, but the simplest way that I like to explain it is constitutional does mean that the configuration of bonds has changed. And so if you have any structure where molecules are hopping around and bonded to new molecules, that's a good example of a constitutional isomer. Sometimes we might see something like, I don't know, an O connected. Well, let me do a better example. Let's go down. So that's one example of a constitutional isomer, as well as there's a couple of other ways we can kind of theorize things. So if I think about this compound here, this is C5O2468. Well, no, let's make them that way. 246810, H10. And so this is an ether, but I could also draw a C double bonded to an O with 5 H's coming off of it. And so in some ways, this one is easier. So there'd be 3 H's here, 2 H's here, 2 H's here, 3 H's here. So 6, 7, 8, 9, 10, 5 carbons, check. 1 oxygen, check. So even these would be constitutional isomers, and those are pretty obvious. It's clearly the bonding has changed. There's something different about the bonding. So constitutional isomers, in my, quote unquote, spend too much time with chemistry opinion, constitutional isomers are fairly easy to identify. You can't, there is something about the molecules that's so clearly not the same, no matter how you rotate the molecule or even think about how things are bonded in space. there should be a clear difference between constitutional isomers. The configuration of bonds has to be different of what they're actually bonding to. Then what a conformer is a conformer requires us to consider that this structure here let's put a Br there, and let's put a Cl here. How do I want to do this? And so we want to kind of be able to rotate molecules about single bonds, because the key to the conformer is that between two structures, if you just rotated a single bond, you should be able to get to the other structure. And so if I draw this example here, and I put my hydrogens back in. Oops. This bond here has been rotated so that the Cl is now pointed down. And so I have a 1095 degrees pointing down, or I have it pointed up, but I've rotated this bond about 180 degrees to the other direction. So now rather than my bromine and chlorine being near each other in a plane with an angle, here 109, here 109, versus here I have my chlorine actually quite far away now from my bromine. And so I have that angle, and then I've changed it over to here. And so these are conformers of one another because I can rotate from one molecule to the other. And so kind of through a rotation of bonds, whether it is a full rotation or if you're doing partial rotations, you are manipulating single bonds to see if you can take one molecule A and see if you can get to molecule B by rotating bonds. Where stereoisomers become a little bit more complicated is that if I do have a Br off to a Cl, down to an H, over to another carbon, and this one will have it go to an OH and have it go out to a, I don't know, fluorine and come back to a hydrogen. I could draw a structure like this where my Br is up here again, my chlorine is down here, my H goes back, bond here, and let's put the H up here. Let's put the OH back here, and let's put the fluorine down here. Between these structures, between structure A and structure B, you'll notice that, or you'll begin to start to see that over here, over here in this area, boom, 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 that is the same orientation that I'm seeing over in molecule B. So that looks like it's the same molecule. But what you're going to notice is that as you try to rotate this around, when H is looking in front of it, it sees this fluorine. Oops, I needed to change this to an OH, or make it more clear that it's an OH. I saw the dotted, or thought it was a dotted line, but this is an OH. Let's just clean it up a little bit. OH. So when this OH is looking in front of it, it sees a fluorine. If I rotate this molecule, if I rotate the OH down here, OH goes there, H now would go in front of it, and fluorine would move over here. So what I've done is I've rotated the bond. Fluorine is now up here, OH is down here, and in front of this OH, when this OH looks ahead, it sees an H. But over here in structure B, when this OH looked ahead, it saw a fluorine. And so these molecules look like they're possibly conformers, that maybe you could rotate this weird end to get it to look like B, but try as much as you can, you'll never get it to look exactly like molecule A. And so you can't rotate it about a single bond to make it into the other one. And then the tricky example we saw in class is that we can take structures that look like this and we can flip them so they look like this, or we could take structures and rotate them and look like that, or I could rotate it this way and make it look like that. There's lots of manipulations where I haven't rotated any single bonds. It always has these two groups near each other in every example I've drawn. I've just changed kind of how I look at it. All of these are the same molecule. I've just changed I've rotated them, I've flipped them, but I haven't rotated about any single bonds. So grabbing the whole molecule, grabbing any whole molecule, whether it's like the complicated molecule we saw on the exam that had, 5-membered rings, things going off to other stuff. All of these molecules, we can grab the whole molecule and we're going to freeze all of its single bonds. We're not going to allow any single bonds to move, and we can do all sorts of stuff with this. We can or flip it. I can't rotate it, but we could if I had a more developed app for the notes and paid for it. But you maybe get my point that, the law or the deceptive simplification of it is these constitutional isomers involve there being these new bond configurations. Atoms are bonded in different ways and often to different things. Atoms bonded to different things. And then a conformer is, I won't say necessarily easy to spot, but certainly over time, if you're asked to say, is A and B a conformer, if you rotate single bonds, can you get to B? Now, you always have to ask yourself, could I have just gotten to B first by freezing all my bonds and just flipping the molecule, rotating the molecule? You might be dealing with a molecule that's identical if you can move it around and flip it around, but a conformer does involve a single bond rotation to actually get to the other structure. And then the stereoisomer is you will have A and B, and no matter how much you flip it, no matter how much you rotate it, no matter how much you mess with single bonds and rotate those things, you'll never get A to look like B. You'll get close. You'll get very, very close. Like we got here, pretty close. Part of the molecule was the same. But part of it, no matter how we flipped the molecule, rotated the molecule, freezing our bonds, or rotating these bonds. And again, if you get to have a model kit, that's incredible. That's a really, really great resource that I'm glad they're letting us use. Because at some point, when you do this long enough, certainly you have a model in your head, but starting out, having these model kits will be a very effective tool for understanding the three-dimensionality of when we're talking about hybrids. It's very important to know what P's were used. I shouldn't really do an X. No, I should do a question mark because what you mixed in matters quite a big deal, and what's left out is making pi bonds. So slightly an oversimplification of it, or slightly an oversimplification of those things, but showing you some examples, and it really comes down to how comfortable are you taking a given line structure. And even here's one with some three-dimensionality in it. I don't know. And are you able to do things like flip it while freezing all your bonds? Are you able to rotate it while freezing all your bonds? And are you able to rotate about single bonds? And that skill, whether you do it on paper or with a model kit, is how you'll start to differentiate between the three isomer types we have right now. And we're going to add to it on Wednesday post-exam. And I think once we add to it, it'll actually become a lot easier. What we're asking you to do right now is a little difficult, but to make it easier, we'd have to make you memorize something else. And I think that's part of why they're moving it to post-exam. But basically, I mean, if you wanted to look it up or you had extra time to study, figuring out how to assign R and S stereochemistry is very, very useful for finding stereoisomers. But that is not a learning objective, even though it is very, very helpful here. And that's probably tantalizing in a mean way, because it's like, I wouldn't recommend for a student who's studying for this exam to look into R and S unless they're very confident about the material and want to realize that it can be made easier and they can prepare for the final. Oh, of course. Thank you for stopping by. All right, I'll be back tomorrow to answer some more questions as you're prepping for the exam. Have a good